Hi everyone, I am Yutaro Mishima, researcher of KDDI Research. It is a great honor to be able to speak to you from Ubiquitous 2021. Today, I'd like to present you our study entitled Is Adding More Modalities Better in a Multimodal Spatio-Temporal Prediction Scenario? A case study on Japan equality. Here's the outline of my presentation. First, I will describe the background and motivation behind this study, followed by our approach and contributions. Some research related to this work will be introduced, and after that, I will describe our datasets. Then, I will present the different experiments conducted and their results. These results are further discussed in order to extend their importance. Finally, I will conclude and introduce our plans about future works. Let me begin by talking about background. Recently, air pollution has grown to be a big issue due to economic activities. Forecasting air quality is important for preventing people from health damage caused by such pollutions. Therefore, it is important to analyze the relation between air quality and human activities for regulating air pollution. Meanwhile, much efforts have been made in order to share spatio-temporal datasets such as air quality for helping researchers conduct various studies. As a result, many novel methods have been proposed in order to manage spatio-temporal datasets. However, these methods are usually scenario-specific, and few of them include functions or blocks designed to capture relationships between the different inputted modalities. This loss of valuable information will prevent models in reaching more accurate performances. Especially, increasing the number and the variety of modalities will probably not allow models to capture more in-depth analysis and achieve significant improvements. In this investigation work, we conducted some preliminary experiments following three questions. The first one to verify previous work affirmation that usual networks such as RNN are said to not work well when inputted data are multimodal. Is this affirmation data scenario specific or valid for any scenario? The second one to determine if recent complex architecture proposals are scenario specific, data specific, or are they generic enough to maintain outstanding performance with any scenario? And the third question, which has a central role in the work, do these complex architectures still perform well when more modalities are included? Or should they require dedicated functions or blocks to capture cross-modal relationships? We conduct three experiments to answer these questions. These experiments are based on a multimodal spatio-temporal dataset composed of air quality, human dynamics, and meteorological data in Japan. We apply multiple methods in order to predict air quality, including one of the latest methods and its variant, where we modify the architecture in order to handle more modalities. As a result, we confirm that prediction performance does not improve when another modality is simply added. That is our main contribution. These insights suggest that some methods are required to explicitly capture complex cross-modal relationships. Before going into the explanation of our datasets and experiments, let me introduce some related research. We pick up four of the latest methods in spatio-temporal prediction. Every method has remarkable results. However, 3 out of the 4 methods handle only 2 modalities. Therefore, it is unclear whether they can handle many modalities properly, while keeping good performance. Indeed, the last one shows that using more than 2 modalities does not improve prediction performance compared with a bimodal scenario. As aforementioned, this study focused on the urban area in Japan, and especially Tokyo and Kawasaki areas as drawn in the figure. Target study period goes from October 20, 2017 to December 2019, which represent 2 years and 3 months of our data. Now let's spend some time on the 3 spatio-temporal datasets used in this study. Air quality is the main dataset. 12 air pollutants such as PM2.5, PM10, and NO2 are continuously monitored by stations all over the country. The study dataset is composed of PM2.5 measurements coming from the 51 monitoring stations within the considered area. The ratio of missing varies for pollutants at the stations. That's why we focus on PM2.5, which is the only one available in all stations and with the least quantity of missing data. Meteorological information is the second dataset. The study dataset is composed of records including temperature, humidity, wind direction, and wind speed from the same monitoring stations and in the air quality dataset. We transform wind direction and speed into horizontal and vertical components in order to avoid transposing wind direction as a linearly independent value by treating it as a categorical feature. Last but not least, we use human dynamics dataset. KDDI Corporation statistically processed GPS logs of its users who gave explicit permission to share their locations. It resulted in human dynamics data, which consists of cell grid level and hourly records. As shown in the bottom left figure, each record has a count of users per activity state, staying in a given location or moving. These counts are normalized on the ratio between the number of users and the total population in Japan. On the right side, we show weekly trend plots of human dynamics in two cells. Blue and orange line respectively correspond to the normalized count of staying and moving users. This figure illustrates the behavior trend varies according to the people location. In the office area, top figure, many people stay during daytime, probably for working, and the count rapidly decreases in the night, most probably because they commute back home. On the other hand, in the residential area, bottom figure, patterns are different. Staying users are greater during night compared to daytime. As illustrated in these figures, human dynamics data can capture people mobility behavior. As illustrated on this slide, the prediction task of this study aimed at forecasting future concentration of PM2.5 for each station and for different horizons going from hour ahead to 12 hours ahead of time. In this problem setting, the input is the past 24 hours of all available data, not only air quality but also when available meteorological and human dynamics data. RMSE is used for evaluating prediction performance, and all stations' evaluation have the same weight in the overall evaluation. Training the models is done on a 1-year period, while validation is done on the next 9 months, and finally testing is performed on the latest 6 months. It corresponds to a 4:3:2 ratio. As mentioned previously, we conducted 3 experiments that I will now present. The first experiment aims to determine if usual neural networks such as GRU or LSTM work well with multimodal inputs data. For that, we compare the prediction performance of GRU and LSTM in 2 conditions. First one, using only air quality data, which is a unimodal scenario, and second, using both air quality and meteorological data, which is a multimodal scenario. Let me add something about parameters. Both GRU and LSTM have only one layer, but learning rates vary for each model and condition in order to obtain the best convergence. Other parameters, such as batch size, heat dimension, are all the same. For more details on the parameters, please refer to our paper. The results of this first experiment confirms that simple models are not good at handling multimodal spatio-temporal data. Regarding GRU, adding one more modality is improving prediction performance for 2 prediction horizons, 1 hour and 6 hours ahead. On the contrary, an additional modality with LSTM is only improving RMC for 1 out of 4 prediction horizons, 1 hour. The second experiment aims to unveil if recent spatio-temporal architecture models are generic enough to provide good prediction accuracy with any dataset while outperforming usual models. For that, we compare the prediction performance of 5 models using both air quality and meteorological data, which is a multimodal scenario. The selected models are historical average, like GPM, GRU, LSTM for the usual models, and DMV-STNet for the complex spatio-temporal architecture. We choose DMV-STNet as it is the only one from the related work providing public source code. In addition, it also ensures reproducibility of our results. Parameters for GRU and LSTM are the same as in the first experiment. I will not go into details of DMV-STNet parameters, but please refer to the paper for that. Now let me describe DMV-STNet architecture, which can handle multimodal dataset. DMB estimate is originally proposed for predicting taxi demand. This method consists of three views: spatial, temporal, and semantic view. The architecture is composed of local CNN to capture spatial relationships among different regions, and of LSTM layer to grasp temporal dependency. Finally, embeddings in a weighted graph to encode similar taxi demand patterns among regions. In our work, we replace taxi demand data with air quality data as shown in the figure. The results of this experiment shows that DMB estimate achieves better performance than 3 out of 4 usual models, historical average, GRU, and LSTM. However, light GBM shows the best performance in 3 out of 4 prediction horizons. The reason behind this interesting result is probably that only light GBM uses some aggregate features, mean, max, average. It may help light GBM capture general trends and lead to greater prediction performance. We suppose that DMB estimate might achieve better performance if aggregate features similar to light GBM were also fed. Finally, the most important experiment in our study aims at determining if recent spatio-temporal proposal can maintain good performances with more modalities. We extended DMB estimate to support one more modality for conducting this third experiment. We call this extended model as EX-DMB estimate. Then, we compare the prediction performance of the original DMB estimates that use two modalities, air quality and meteorological data, with our EX-DMB estimate that uses three modalities, air quality, meteorological, and human dynamics. Regarding parameters, we changed the batch size and learning rate in EX-DMB estimate due to GPU limitations. The other parameters are exactly the same as the original DMB estimate. Now, let me describe our extension of DMB estimate. In this figure, blocks that are drawn with bold type letters and a dashed border are part of our extensions in order to include human dynamics as input from the original DMB estimate. In EX-DMB estimate, human dynamics is treated like air quality. It is fed into new local CNN. The output is concatenated with other features, the output of air quality, local CNN, and context features generated from meteorological data. The resulting concatenation is then inputted into the LSTM layer. In parallel, human dynamics is also used to generate a weighted graph of human dynamics by calculating similarities between human dynamics patterns of two cells. The results of this third experiment confirms that EX-DMB estimate, which is an extension of the recent spatio-temporal method, cannot fully benefit from the potential of human dynamics when predicting air quality. Here, prediction error increased in 3 out of 4 prediction settings when human dynamics data is added. Moreover, the improvement for the last prediction horizon is under 0.3%, which is not significant. These results are interesting in many ways, but we can further discuss them. First, our experiment shows that handling multimodal inputs is complicated. From the result of third experiment, we confirmed that simply adding new modalities to prediction models does not guarantee an improvement in accuracy. Even recent proposed models are not generic enough in order to handle any number of multiple modalities. Therefore, we need a generic mechanism which enables a given architecture to achieve significant performance improvement using any number of modalities. The mechanism should learn not only about the relationship between each modality and the target, but also about cross-modal relationships. For instance, it could be done by adding a block designed to capture cross-modal combination and to determine how modalities affect each other. In addition, meteorological data has a unique position compared to other used datasets. Indeed, its relationships with other modalities may dynamically change. For example, the wind direction and wind speed may affect which surrounding cells of human dynamics data will impact the PM2.5 concentration level of a given cell. A potential solution will be to model propagation of PM2.5 in the atmosphere based on wind speed and direction, such as discussed in a recent paper. Of course, this alone does not solve the cross-modal issue, and it should be combined with the previous proposal. Furthermore, one could argue that the effectiveness of human dynamics data in air quality prediction has never been proved. Even though it is straightforward to conceive such a relation, it is still necessary to quantify it. For that matter, we investigate correlation between human dynamics and air quality. As a result, we find that a correlation exists between air quality and human dynamics, even though it is complex as it depends on time, location, and delays. Let me present two figures illustrating correlation levels between number of moving people and air quality for a 5x5 grid cells. Red and blue shading represents the range of correlation from high to low respectively. The upper figure indicates correlation during commuting hours, and the lower indicates that during midnight on weekdays. We can clearly see that correlation is stronger along main road during commuting hours compared to midnight. This probably captures the impact of car gas emission onto air quality. It also suggests that time is playing an important role in correlation. Finally, from these results, we discover an issue regarding human dynamics definition. Currently, human dynamics data are mixing means of transportation regardless of whether those have a positive or negative impact on air quality. Therefore, we require human dynamics data that separate moving people based on their transport modes. Such data should help model better predict air pollution. Now, let me summarize this presentation. First, our study unveiled a common and significant problem among recent multimodal spatio-temporal methods. Indeed, it shows that adding more modalities does not guarantee an improvement in spatio-temporal prediction, even though the additional modalities have an effect on the predict data. We also confirm that recent deep learning architecture models might not be able to capture complex cross-modal relationships in any scenario. As a future work, we will propose a novel architecture that can handle cross-modal relationships even though many modalities are inputted. There is two ideas for such a proposal: using specific attention layers to capture cross-modal relationships and combining it with an explicit propagation model of air pollution in the atmosphere. Moreover, for more practicality, we will consider providing a way to interpret these cross-modal relationships, for example using visualization of attention weights. This is all for my presentation. Thank you so much for your kind attention.